Now let's see how are we going to distribute this? How are we going to parallelize this, right? What we're going to do is we are going to look at a 2D distribution. So what will a 2D distribution looks like? Okay, it's quite natural, a 2D distribution in this case. We'll divide the P processors into a root P cross root P processor grid. And of course, our adjacency matrix or any of the D matrix, right? They are all of size n cross n. Right. So how am I going to distribute the matrix, the adjacency matrix across the processors in a 2D distribution? So I'll have my processors will be numbered, using two indices. So P00, P01, right? And the last one would be P0 root P minus 1, right? Is that okay? And then you'll have P10, P11, and so on, and all the way down. The last one over here will be P root P minus 1, comma 0, right? And so on. Yeah, is that clear? So that's just the numbering, the 2D numbering for our processor grid, right? And now I'm going to distribute this matrix over these processors. So the matrix is n cross n. So obviously, what goes to each processor? It's n by root p rows and n by root p columns, right? So just an equal division. All right. Now, how many elements are there on each processor? That's n by root p into n by root p, which is n square by p, right? So total n square elements, they're divided amongst p processors. Obviously, each processor will have n square by p elements. Okay. So we are going to store n by root p cross n by root p blocks on each processor. All right, let's consider what happens in a particular iteration, right? In a particular iteration, let's say when we are computing dk, right? Let's look at one particular entry. So this is your dij of k. Well, okay, let's not worry too much about the k, right? So let's say I'm in the kth iteration, right? Let's say I have dk minus 1. This is my matrix dk minus 1. Now I'm going to update my ijth entry. So actually, I won't be updating the ijth entry over here, right? I'll be updating it in a separate matrix. dk minus 1 is a separate matrix from dk. This is the matrix dk minus 1. But just for the purpose of illustration, I'm just showing it in the same matrix. Okay. So I'm actually updating this in some other matrix. But let me visually try to see what are the dependencies, what are the elements that I want. Okay. So there is this k minus 1th row, right? And this is the element. So which element would this be? This would be the k minus 1th row, jth element, right? From the matrix dk minus 1. Yeah, I'm dependent on this element. And similarly, if I look at the k minus 1th column, right? There's the element sitting over here. What is this element? This element is di. Sorry, I'm interested in I'm interested in kth row. Okay. If I'm in the kth iteration, I'm interested in dkj, right? And similarly, I'm interested in the kth column. Okay. So I'm interested in dik. But both of these are coming from the matrix dk minus 1. Yeah, is that clear? So essentially, I'm dependent on this and I'm dependent on this. These are the elements that I want in order to compute dijk, right? Just two elements. All right. Now, let me just extend this a bit, right? So actually what's going to happen is that I'm not going to do communication for every element that I'm updating, right? So let's have a look at a particular processor. Over here, we were looking at it from the perspective of a particular element. Now let's have a look at it from the perspective of a particular processor. So this is my processor. So I'm going to use a different notation for processor indices than I'm using for element indices, right? So let me use the notation PLR. This is the processor PLR. L and R vary from 0 to root n minus 1. Yeah, is that okay? This particular submatrix, I'm going to refer to it as DLR. This is the entire block or submatrix stored at PLR, right? You can calculate the indices for this. You can do it on your own, okay? So it's just basically L times n by root P up to L plus 1 times n by root P minus 1. Yeah, and same for R. It's basically a n by root P by n by root P block, right? At the appropriate coordinates. Okay, so let me work with this block. So I want to update this entire block DLR, right? Residing on processor PLR. So what do I need for this in the kth iteration? Again, I'm talking about the kth iteration. So what do I need for this? I am going to need from the kth row, I'm going to need this entire vector. It's not a block, it's just a vector, which is part of the kth row, right? So I'm just going to need this vector. And similarly, if I see down here, I'm going to need this vector from the kth column. Is that clear? What notation can I give it? Well, I can call this as D of kth row and the entire R. The range of R is the entire R, right? Sorry, K and R are looking a bit similar over here, but the first index is K. K is referring to one index, right? R is referring to an entire range of indices. Is that clear? I'm just using that capital notation to, it's essentially encoding a range of indices, right? That's what it's doing. That's what this DLR is. It's n by root P sized range. Any confusion around this? I hope there is no confusion around this, right? And similarly here, this would be DLK. Yeah, so basically if both the indices are small alphabets, then it's an element. If both of them are capitals, then it's a block. And if one of them is capital and one of them is small, then it's either a row vector or a column vector. So now with this notation set up, right, let's go ahead and try to write the algorithm. This processor PLR is going to require this vector. So you don't have to transfer an entire blocks, right? You just have to transfer a vector of n by root P elements. This is only of size n by root P, right? It's a vector. And this is also size n by root P. So you only have to transfer vectors of size n by root P to PLR. Yeah. Let's just turn this around, right? Instead of looking at from the perspective of one block, well, PLR needs this, but actually every processor will need some information, right? So the processor here will need this DKR, another one will need DKR, this processor will need DKR. There are multiple processors along this column, right? All of them will need DKR. So actually this DKR, this vector is going to be broadcast to all the processors along that column. Yeah, because what about processor PL minus 1R? That also needs the same thing, DKR. It also needs DKR to update DL minus 1R, right? And so on. So no matter what the first index is, that processor is going to require DKR in order to do its updates in the kth iteration, right? And similarly, this DLK, any processor along this row is going to require DLK. Yeah, clear? And that's not just restricted to this row. There is another vector sitting over here. What about this processor sitting over here, just above DL minus 1R, the one we were talking about? Well, it requires DKR, which happens to be the same one. But what about the column vector? Which column vector does it require? It doesn't require DLK, but it requires DL minus 1K, right? So similarly, you're going to broadcast this, right? And then there's some vector here, right? Is this clear? Okay. So each processor in the kth row and the kth column is going to broadcast its vector along the respective row or column. right? And then all the processors will receive one vector from their row, one vector from their column, and they'll do the updates. Right? Okay. So now let's write the pseudocode for Floyd's Studi algorithm. Floyd with 2D data distribution. Again, we'll take the same input, adjacency matrix A, right? And let me write the code for processor PLR, right? So let's assume that we are sitting on processor PLR. So actually what this A you're getting is just the part of A which corresponds to LR. So how do you start? You start with D0, let me just denote it as LR is equal to ALR. And then I'm going to run the same loop as I did before. I have to work in iterations for K is equal to 1 to N. And now what I'm going to do is I'm going to check if my processor contains a part of the kth row or the kth column, right? Because then I'm responsible for doing broadcasts. Okay. So first let me check if K belongs to the range R times N by root P up to, okay, if we are using indices starting from 1, yeah, then you may have to code this slightly differently, right? So you'll have to add 1 over here, and you still assume that L and R range from 0 to root P minus 1. But your indices start from 1, so you'll go from R times N by root P plus 1 up to R plus 1 times N by root P, right? That is the range. So you check if your column, right, R is the column, if your column is in this range, right? Then what you're going to do is broadcast. So if you own this part of the kth column, then you broadcast DLK K minus 1 to all the processors along the row. Broadcast along row. You're sending it to everybody irrespective of what the column index is, right? Everybody in the LH processor block row. Broadcast part of kth column, right? And the broadcast will happen along the row, right? So you're broadcasting a part of the kth column along the row of processors. Okay, so if K is in my range, right? If I am the owner of the kth column, then I have to do a broadcast of my part of the matrix, right? And if I'm not the owner, then I have to receive it. Okay. All right. Similarly, I have to do exactly the same thing now with the row vector, right? So if K belongs to L times N by root P plus 1, L plus 1, N by root P, yeah, then I will do a broadcast. So if I'm the owner of some part of the kth row, then I'm going to broadcast D KR K minus 1 to P star R, right? So I'm basically doing a broadcast along the column of processors. Else, I will do a receive DKR K minus 1. Clear? And finally, when I have all this, then what do? I compute, I basically do the computations for DLR. I have all the data that I need for DLR, so I go ahead and compute DLR. Right? So what is the computation of DLR? That's the same as Floyd's algorithm, right? You just run a loop over the range of L over the range of R, and you just update the entries using exactly the same rule. You have all the dependencies with you. Okay. Clear? Any questions on this algorithm? This is it. This is your 2D algorithm for Floyd's with 2D distribution, right? Yeah, any questions, guys? This is the end of the algorithm. Let's do a little bit of an analysis of this. So how much time is taken in computation? When I compute DLR, how many elements am I updating? that is going to be n square by p, right? So I have to update n square by p elements. That's a grid of size n by root p by n by root p, right? So n square by p elements. And there are n iterations in all, right? So total time is going to be n cube by p. And what's the communication time? What is the size that I'm broadcasting? The size that I broadcast is n by root p elements, right? 2n by root p. Well, I'm again working with asymptotic notation, so I don't care about the 2. N by root p elements. Is that correct? So how long does it take to broadcast n by root p elements? We'll assume that we have enough bisection bandwidth. So if you have, let's say these are my 8 processors, and I want to broadcast something from this node to all the other nodes, right? So typically what do? Typical algorithms, what they do is they run in log p iterations. That's a standard class of MPI algorithms, right? In the first iteration, what will it do? It will send this message to the fourth. Let's number these P0, P1, P2, P3, P. I'm just taking an example, okay? P0 to P7, right? There are 8 guys. So in the first iteration, you send it to P4, right? And then in the second iteration, you send it to P2, and P4 simultaneously sends it to P6. So in the third iteration, you send it here. Now 4 guys have the data, so you can do 4 sends simultaneously. Yeah, and that's it. In 3 iterations, you're done. So clearly it's a log P algorithm, right? Again, there are different algorithms, and particularly if you have different architectures. For instance, let me just give you an example. If you have, let's say, a 2D mesh kind of architecture, right? So this is, let's say, root P by root P grid, and you map it exactly so that each column over here in the physical processor grid corresponds to your logical processor grid, right? So then if you had to do a broadcast from this node, these are all kinds of actual optimizations that are done in physical networks. So you put it on this link, right? You can do a link level broadcast, okay? And when you do that link level broadcast, within the same time, you can actually get that data on all the nodes, okay? You save that log P. That's kind of like the motivation for why supercomputers are typically built using 2D, 3D grids, because the real world is 3-dimensional. And if you're trying to solve problems in the real world, such as, let's say, weather modeling or something, right? You're actually dealing with 3 dimensions, right? And you do the communication along the latitude, longitude, and vertical, right? So if they map to your grid nicely, then you can do that communication very quickly. But those kind of algorithms, you have to design it for particular architecture. So if you're given a particular architecture, you can build an MPI library which performs very well on that given architecture. But if you download a generic MPI library, OpenMPI or any other generic library, right, they don't assume anything about the underlying architecture. They cannot, right? So in that case, they use these kind of algorithms which are generic. So what is the communication time? We'll stick to this. So this is theta n by root p log p. And you have to do this in every iteration, right? So there are n iterations, right? So this is theta n square by root p log p. Okay. So what is your speed up? Speed up is n cube was the sequential time. And this is going to be theta n cube by p plus theta n square log p by root p. Okay. So you can simplify this further, right? Let's look at the efficiency. You just divide the speed up by p, right? That's how you get efficiency. So this is going to be something like 1 upon 1 plus. So you multiply this by p and you're dividing by n cube. So this will become 1 plus theta. So you'll get root p on top. Log p remains there. And then because you're dividing by n cube, you get an n at the bottom. Yeah, you're dividing by n cube because you're trying to make the numerator 1. Okay. So that's your efficiency, right? I hope you guys remember, right? How do you calculate efficiency? It's basically speed up divided by P. So what does this mean? This means that, this algorithm will work quite well. You'll get θ1 efficiency if your processors are no more than n square by log square n. Okay. You can substitute this and check, right? It's coming from this expression only. If P is n square by log square n, root P will become n by log n, and log P will become log n roughly. So log n cancel out, and n will cancel out. Okay. So it's quite good. I mean, typically n is much, much larger than P, right? Again, this is just for theoretical interest. In practice, n is much larger than P. So this algorithm is quite good in practice, right? Works quite well. Okay. So that's your Floyd's algorithm for shortest path.